Okay, hi calculus. So here is my promised screencast review of the problems that I gave you today in class. A couple of things. Remember, okay, I wrote a lot of this out here. Remember, if you have a convergent geometric series, okay, if you have a convergent geometric series, you are able to find the value of that convergent infinite series if you're asked to, right? It's the only kind of convergent infinite series that we have an easily readable way to find that infinite sum. And that just comes from, if you look at your notes, it's been a while, I know, and today I could see, it's been a while. Right? If a geometric series does converge, and if the question asks you, not only does the series converge, but if it does converge, what's the convergent value? You can find it right here. So for question number 1, when you're asked to find f of 0.2, all I did here is write a few terms out, and you can see here that r is tan of 0.2. This is where you do use your calculator. Tan of 0.2 is this number right here. Notice this number is between -1 and 1, so the series converges. And since this question asked you to evaluate this quantity, right? Evaluating this quantity means finding the value of this infinite sum. And that infinite sum is none other than right here, the first term all over 1 minus r. So there's the convergent value, all right? Just some old stuff. I know there's a couple of things going on. This is the time of year. It's January and February. I call it every year. It's the armpit of the school year. It's the most difficult part of the school year because you're feeling the crush. Just all your classes are getting harder, and just at the same time, the weather outside just looks like, a gray crayon vomited on our world. It's difficult, okay? I'm going to go to question number 3 for a second. These are 3 series, and look at the wording. The question just says, which of these series converges to 2? And already that wording, converges to 2, kind of gives you a hint that we're going to be involving a geometric series somewhere, because no other infinite series other than a geometric one are we able to find its sum, okay? So first of all, question number 1, that series diverges by divergence test. Series 2 and 3, you'll notice they're both geometric and they're both convergent. I don't have the problem set right in front of me because I just walked into the other room to record this, but when you look at those 2 convergent series, compare their convergent values, which means evaluate this. One of them, maybe both of them, or is it one of them, will equal 2, and maybe the other one won't, okay? Going back to number 2, question number 2 is about a sequence, and you're asked to determine its monotonicity. Of all the monotonicity tests, and there are 3, the easiest, okay, the easiest is looking at the sign of f prime, right? And I think, again, I don't know, is the series in front of me? I don't think it is, but I think in this case, was it this? N plus 4 over n? Was that it, possibly? I can't remember. Anyway, this is the sequence. So when you use the derivative test, what you do is you say, okay, let's create a continuous function, and then let's take its derivative. Okay, and then let's figure out the first derivative critical points. Okay, and Vishnu, for some reason, oh yes, never mind, I did this with Vishnu. When you get here at the end of the day, I think you get x equals plus or minus 2 after you solve, right? But again, for this sequence, I believe the sequence is only for values of n, integral bigger than or equal to 1. So the positive 2 is all I really care about. So I'm going to go down here and do a first derivative sign analysis for values of x less than 2, f prime is positive, and then it becomes negative. So, and remember, with sequences, eventual behavior is what matters. So from the second term on, this sequence is eventually strictly decreasing because f is decreasing, okay? So of all the monotonicity tests, the f prime one is the easiest, okay? All right, here's number 4. I promised I'd do out for you. So question number 4, here's the setup. So let's just look at that part of it first, okay? So these are my coordinate axes right here. Okay, the x and y axis. I graphed the curve y equals e to the negative x squared only in quadrant 1. This point here is y equals 1. And yes, look at this interesting behavior here. This curve does, forever approach the x-axis. And so if this question asked you to evaluate this volume, you'd have to use an improper integral, but I'll show you that in a second. Okay, so this is the curve. This is the area that they describe, I believe, right? In quadrant 1 between y equals e to the negative x squared and the x-axis. And then here is the revolved image. So we're revolving around x equals -2. So here is the image of this region being revolved, okay? And this green right here, I just sketched in a cross-section of this solid. The black here, everyone, is big radius, small radius. Look at that. So then when I'm looking at this, everybody, I'm just going to do a little bit of a gentle review of volumes. How are the cross-sections stacked? Cross-sections are stacked vertically, aren't they? They are stacked vertically, which means I'm going to need an integral in terms of what, everyone? Yes, y, integral in terms of y, which means my dummy is what, everyone? dy. Maybe some of you are talking in unison with me. Okay, and what's the interval of integration? What's the interval over which these cross-sections are stacked? Yes, they are stacked over the interval from 0, although 0 is kind of like this limiting value, to 1. All right, so now I have I'm going to go down here. Maybe I wrote down the dy, maybe I wrote down the 0 and I wrote down the 1. And now I'm saying, okay, what's the integrand? All right, look at this big black length. That is the big radius. Well, the first thing I have to do here, since we're in the world of integrals with respect to y, I have to take my curve, solve it for x. Look at that. Very good. Now, x equals -ln y, everybody. You know what this distance is? That distance is just this one, everyone. That's just this, from the distance from the y-axis to the curve. This is that distance x. We have to add, though, this to it. So the big radius is -ln y plus 2. What's the small radius? Can you see the small radius is always 2? Very good. So the volume is going to be the pi, remember, don't forget pi r squared minus pi r squared. Pi times the definite integral 0 to 1, big radius squared minus small radius squared, dy. There it is. Very nice. If this question were going to ask you to evaluate, one would have to recognize that, oh, this is an improper integral. So if I were to evaluate this, I would have to introduce a limit. The limit as b approaches 0 from what side, everyone? From the left or from the right? Yes, from the right, of pi times the definite integral of b to 1 of all of this jazz dy, okay? Improper integrals, though, that's a blast from the past, okay? Okay, the second part of this question was the same region. I'm going to go over here and sketch it and do it with you in live time. How about that? Okay. This question said they want the region, I believe it was it 1 to 9? I find it so funny sometimes when I sit here and I talk to you as if anyone could actually answer me. I think it's x equals 1, x equals 9, y equals 0, which is the x-axis, and the curve, right? Was that right? Yeah. Okay, and then here is my region, okay? So my region is right here, and this one is one of those base of a solid questions. This is the base of a solid whose cross sections. How are the cross sections oriented, Thomas and Tyler? Yes, parallel to the x-axis, not the y-axis. So what that means is, if I were to try and sketch a cross-section, it means that I have like semicircles popping out like this, right? Parallel to the x-axis, okay? Now, something very interesting is going on here, because if you look at my semicircles, right, if the interval of y is below this point, so from here down, my semicircles all have this constant diameter. Okay, it's a constant diameter. Then when I get above this intersection point, my semicircles then don't have a constant diameter, right? That's when the diameter of the semicircles is going to depend on this function. Okay, either case, be that as it may, we definitely know, look, if you look at the cross sections, we've got an integral in terms of y. And here's the thing, you know what? We have two integrals in terms of y. I need two because the radius or the diameter of the semicircle is defined by different curves, right? I mean, it's defined by this curve. Then I'll pan back to get what that curve is. But then below this point, it's just defined by the vertical lines x equals 9 and x equals 1. Comprende? So the first integral with respect to y is going to be the interval of y from 0 to whatever that point is. Because this point here, right, corresponds to this point here. And we'll figure that out. I'll even put 0 to question mark, right? And the second integral is going to deal with these light blue cross-sectional shapes that are existing over the interval of y from, well, this question mark place to this place, and that's 1. So I'll do question mark to 1, okay? Now, the first integral is nice and easy because I'm looking at, let's just go down here and do this, and let's just be very methodical about this. Okay, I need to find the area of one semicircle. In general, the area of one semicircle is 1/2 of pi r squared, right? Yeah, very good. Right? Yes, because pi r squared is a whole circle, a half. Yes, give me a minute. I just had a brain burp. And in this case, the radius is 4. Agreed? So it's 1/2 of pi times 4 squared, which is 16. This becomes 8 pi. So right here, that's the area of the of a semicircular cross section from y equals 0 to y equals question mark. Okay, I'm going to go walk to my calculator and actually find what that question mark point is because we need it. Okay, here I am. Well, I can't find my calculator, so we're just going to do this all in exact form, not a problem whatsoever. So if this value is x equals 9, then this point here, you know what that point has to be? That point has to be 9 comma e to the negative 81st, right? All I did was just plug that in to the function right here. Okay, no big deal. That's fine. So now at least I have my limits of integration, e to the negative 81st. This is going to be e to the negative 81st. This wasn't calculator active after all, Allison and Melissa. Okay, so now let's deal with the semicircles up here in this region. So here's what's interesting, right? When we look at this curve, okay, and let's just go back and let me get the curve here. This curve here is x equals negative, no, what is it again? Let me go back and look. Okay, this is x equals the root of negative ln y, right? Okay, so everyone, this distance right here, the diameter, that distance is the root of negative ln y minus 1. Would you agree that's this distance here, right? Now follow me. That means the radius of this semicircle is root of negative ln y minus 1. Boink, all over 2. That's then the radius of each of those semicircles. You follow, everyone? Okay. That means the area of each of these, is 1/2 pi r squared. And there is our integrand, okay? There it is. So I'm just going to pop that in. Let's pop it in. See if I can get all in one screen. I'm going to pop this into here. Okay, I may have to move some things over. Let's see. Okay, here we go. I'll pull the pi over 2 out. Okay, good. Okay, negative, oh my gosh, how embarrassing. Okay, root of negative ln(y) minus 1 all over 2, all of that squared dy. Okay, now this was just set up the integral expression only. Don't you dare, anyone, don't you dare do a thing where you square this square root and say, oh, it undoes each other. No, 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 it doesn't, because of this -1 hanging around the party, okay? But there it is, okay, as promised. I hope that was helpful. Look over our stuff, okay? We're nearing the end here, everybody. Well, actually not even close, so disregard that. Never mind. Okay, goodbye.